To calculate voltage drop, we use the formula voltage drop equals the length of the conductor times the current times the resistance per unit length, all divided by 1000. In this specific example, the length of the conductor is 600 feet, the current is 400 amps, and the resistance per unit length depends on the conductor type and size. For a 600 cmTW insulated conductor, the resistance is approximately 0.597 ohms per 1000 feet. Now, we can substitute these values into the voltage drop formula. Voltage drop equals 600 feet times 400 amps times 0.597 ohms per 1000 feet, all divided by 1000. This calculation results in a voltage drop of 14.33 volts. To determine the voltage drop percentage, we use the formula voltage drop percentage equals voltage drop divided by the source voltage, then multiplied by 100%. In this case, the voltage drop is 14.33 volts and the source voltage is 208 volts. So, the voltage drop percentage is 14.33 volts divided by 208 volts, multiplied by 100%, which equals 6.89%. Therefore, the voltage drop for 600 cmTW insulated conductor with a length of 600 feet, carrying 400 amps on a three-phase 208 volts system is approximately 14.33 volts with 6.89%. Let's explore the components of the voltage drop formula in more detail. Firstly, the length of the conductor is a critical factor. The longer the conductor, the greater the voltage drop. This is because the resistance of the conductor accumulates over its length. Secondly, the current flowing through the conductor directly influences the voltage drop. A higher current will result in a larger voltage drop because more electrons are moving through the conductor, encountering resistance. Thirdly, the resistance per unit length is determined by the conductor's material and size. Conductors with lower resistance materials, such as copper, will have less voltage drop than conductors with higher resistance materials. Similarly, larger conductors have lower resistance per unit length than smaller conductors. The resistance per unit length value is typically found in tables provided by cable manufacturers or electrical codes. These tables specify the resistance for various conductor sizes and insulation types. For instance, the resistance of a 600 cmTW insulated conductor is different from that of a 600 cmTHHN insulated conductor. The insulation type affects the conductor's operating temperature, which in turn affects its resistance. The formula voltage drop equals length times current times resistance per unit length divided by 1000 provides the voltage drop in volts. The division by 1000 is necessary because the resistance per unit length is usually given in ohms per 1000 feet. By calculating the voltage drop, we can determine if it falls within acceptable limits. Electrical codes and standards typically specify the maximum allowable voltage drop for various applications. For example, the National Electrical Code, NEC, recommends a maximum voltage drop of 5% for feeders and branch circuits. If the calculated voltage drop exceeds the allowable limit, several actions can be taken to reduce it. Firstly, the conductor size can be increased. A larger conductor will have a lower resistance per unit length, reducing the voltage drop. Secondly, the length of the conductor can be shortened, if possible. A shorter conductor will have less overall resistance, resulting in a lower voltage drop. Thirdly, the current can be reduced by redistributing the load or using more efficient equipment. A lower current will directly reduce the voltage drop. In addition to these measures, other techniques can be employed to mitigate voltage drop. For example, voltage regulators can be installed to maintain a stable voltage level. These devices automatically adjust the voltage to compensate for voltage drop. Another approach is to use multiple parallel conductors instead of a single large conductor. This effectively reduces the resistance of the circuit and lowers the voltage drop. It is also important to consider the impact of voltage drop on equipment performance. Excessive voltage drop can cause equipment to operate inefficiently or even fail prematurely. Motors, for instance, may overheat and have reduced torque if the voltage is too low. Electronic devices can also be sensitive to voltage variations and may malfunction if the voltage falls outside their specified range. Therefore, it is crucial to carefully calculate and mitigate voltage drop to ensure the reliable and efficient operation of electrical systems. Understanding the voltage drop formula and its application is essential for electrical engineers, electricians, and anyone involved in the design, installation, and maintenance of electrical systems. By accurately calculating voltage drop and implementing appropriate mitigation measures, we can ensure that electrical systems operate safely and efficiently. In summary, the voltage drop formula is a fundamental tool for analyzing and optimizing electrical systems. It allows us to determine the voltage drop in a conductor based on its length, current, and resistance per unit length. By understanding the factors that influence voltage drop and employing appropriate mitigation techniques, we can ensure the reliable and efficient operation of electrical equipment and systems. Remember to always consult relevant electrical codes and standards when designing and installing electrical systems. These codes provide guidance on acceptable voltage drop limits and other safety requirements. By adhering to these codes, we can ensure the safety of people and property. Furthermore, it is important to use accurate data when calculating voltage drop. The resistance per unit length value should be obtained from reliable sources such as cable manufacturers' catalogs or electrical code tables. Inaccurate data can lead to incorrect voltage drop calculations, which can have serious consequences. In addition to the basic voltage drop formula, there are more complex formulas that take into account factors such as power factor and conductor spacing. These formulas are typically used for more detailed analysis of electrical systems. However, the basic voltage drop formula provides a good starting point for understanding the concept of voltage drop and its impact on electrical systems. In conclusion, voltage drop is an important consideration in electrical system design and operation. By understanding the voltage drop formula, its components, and its implications, we can ensure the reliable, efficient, and safe operation of electrical systems. Always remember to consult relevant electrical codes and standards and to use accurate data when calculating voltage drop. The specific formula we used, voltage drop equals length times current times resistance per unit length divided by 1000, is a simplified version often used for single-phase circuits or balanced three-phase circuits where the conductors are close together. For more complex scenarios, such as those with significant inductive reactance or unbalanced loads, more sophisticated calculations are necessary. Inductive reactance becomes a factor when dealing with alternating current circuits, especially over longer distances or with larger conductors. The inductive reactance contributes to impedance, which is the total opposition to current flow in an alternating current circuit. The voltage drop calculation then needs to account for both the resistance and the reactance. The formula for voltage drop in such cases becomes more complex, often involving vector calculations to combine the resistive and reactive components. Power factor also plays a crucial role in voltage drop calculations in alternating current circuits. Power factor is the ratio of real power, measured in kilowatts, to apparent power, measured in kilovolt amps. It indicates how effectively the electrical power is being used. A lower power factor means that more current is required to deliver the same amount of real power, leading to increased voltage drop. To compensate for low power factor, utilities often encourage or require customers to implement power factor correction measures such as installing capacitors. These capacitors counteract the inductive reactance in the circuit, improving the power factor and reducing voltage drop. Unbalanced loads in three-phase systems can also complicate voltage drop calculations. In a balanced three-phase system, the loads on each phase are equal and the currents are equal in magnitude and 120 degrees apart in phase angle. However, in an unbalanced system, the loads and currents are unequal, leading to voltage imbalances and increased voltage drop. To accurately calculate voltage drop in unbalanced systems, it is necessary to analyze each phase separately and consider the interactions between the phases. This often involves using symmetrical components or other advanced techniques. Conductor spacing also affects voltage drop, particularly in alternating current circuits. When conductors are spaced further apart, the inductive reactance increases, leading to higher voltage drop. This is because the magnetic fields produced by the conductors interact less effectively when they are further apart. To minimize inductive reactance and voltage drop, conductors are often bundled together or placed in close proximity. The type of wiring method used can also influence voltage drop. For example, using conduit can affect the heat dissipation of the conductors, which in turn affects their resistance and voltage drop. Similarly, the presence of other conductors or equipment nearby can affect the electromagnetic environment and influence voltage drop. In addition to these factors, the operating temperature of the conductors must also be considered. The resistance of a conductor increases with temperature, so voltage drop will be higher when the conductors are hot. Electrical codes specify the maximum allowable operating temperature for different types of conductors and insulation. It is important to ensure that conductors are not operated above their rated temperature, as this can lead to insulation breakdown and other problems. When calculating voltage drop, it is also important to consider the voltage drop in the neutral conductor. In single-phase circuits, the neutral conductor carries the return current, and any voltage drop in the neutral conductor will add to the voltage drop in the phase conductor. In three-phase systems, the neutral conductor may carry a significant amount of current if the loads are unbalanced. To minimize voltage drop in the neutral conductor, it is often sized larger than the phase conductors. Another important consideration is the voltage drop in the grounding conductor. While the grounding conductor is not intended to carry current under normal operating conditions, it may carry a large amount of current during a fault. It is important to ensure that the grounding conductor is sized adequately to minimize voltage drop during a fault, as this can affect the operation of protective devices such as circuit breakers and fuses. The voltage drop calculation is an essential part of the electrical design process. It helps ensure that electrical equipment receives adequate voltage to operate properly and that electrical systems are safe and reliable. By carefully considering all of the factors that can affect voltage drop, electrical engineers and electricians can design and install electrical systems that meet the needs of their customers and comply with all applicable codes and standards. Therefore, while the basic formula provides a good starting point, it's essential to understand the nuances and complexities that can arise in real-world applications and to use more sophisticated calculations when necessary.